Hi y'all, welcome to 3.1. Today we are going to start our study of rational functions, and we're going to look at all the different features of the graphs and be able to find those values and features and be able to sketch those graphs. So, rational function is a function with a variable in the denominator. So it's going to be a fraction. It's going to have an x, or whatever letter we're using, in the bottom of it. So the parent function is y equals 1 over x. And here is its graph. And you notice it has two pieces. Also, it has a vertical asymptote and it has a horizontal asymptote. And those are going to be really big deals on rational functions. So if we look at a few other shapes that rational functions can take, if we look at this first one, it's in 3 parts. And again, thinking about asymptotes, we've got a vertical asymptote here at -5. And we have another vertical asymptote at x equaling 2. And it also has a horizontal asymptote at y equals 0. So our graph will approach those lines, but it won't cross those lines. If we think about the domain, it breaks at -5 because that's a vertical asymptote. It also breaks at x equaling 2 because that's a vertical asymptote. The graph is totally undefined at the vertical asymptotes. Also, from limits, the limit of f of x as x approaches negative infinity. Negative infinity on the x-axis is the far, far left edge of the graph. And if we look at the far left edge of this graph, we see our graph is approaching that horizontal asymptote, HA, horizontal asymptote of y equals 0. So that limit is 0. Then on the other limit, the limit of f of x as x approaches positive infinity, that is the far, far right edge of the graph. And on the far right, again, we are approaching that horizontal asymptote of y equals 0. If we look at the second one, again, noticing some asymptotes, we have a vertical asymptote here at -5. So the domain has a break at -5. And these limits are asking what the limit of f of x as x approaches -5. -5 is a vertical asymptote. And that negative sign means on its left. So if we look at this vertical asymptote, label each side of it, each end of it, left, right, we see on the left side, there's nothing up top, but on the left side, there is something on the bottom. On the left of that vertical asymptote, as the graph gets closer to that asymptote, it's going down. So that is approaching negative infinity. And then on the right side, limit of f of x as x is approaching -5 on the right, that positive, it's still a vertical asymptote, and we are looking at the right side of the vertical asymptote. So if we look just immediately to the right of our dashed line, our graph as it gets closer to it is going up, 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 up on the right. So that limit is positive infinity. Now, let's take a look at another shape that can happen. This looks like a line with a hole in it. And we're going to discuss in this lesson why those holes happen and what to do about them. So we notice this hole is at x equals 4. So the graph does not have a value at x equals 4. So its domain, left to right, would start at negative infinity, and it would go to 4, not including 4, so it's a parentheses. Then we start over on the other side of 4 and go to infinity. Because of that hole, the domain breaks at x equaling 4. And then if we look at the limits this is asking, the limit of f of x as x approaches negative infinity, x approaching negative infinity is the far, far left of the graph. So on the far left of the graph, we look at what the graph is doing. It's going downward. So that is going to be approaching negative infinity. Then on the far right, as x approaches positive infinity, it's going to be on the far, far right of the graph. If we look at what's going on the far, far right of the graph, the y's are going up. So that's approaching positive infinity. Now, let's look at this last one. We see something a little different going on here. We do notice we do have a vertical asymptote here at x equaling -2. So our domain will break, not exist, at -2. So that piece on the left is from negative infinity to -2. And then we start over on the other side of -2 and go to infinity. So there is our domain. Now, if we look at the limits, it's asking us for the limit of f of x, that's the y's, as x approaches -2 on the left. So that is a vertical asymptote at -2, and we are looking at its left side. So left side, right side of that vertical asymptote. On the left of the vertical asymptote, just to the left of that dashed line, the graph does exist. And as the graph gets closer to that asymptote, it's going up. So on the left side, that limit is positive infinity, because on the left side of that asymptote, the graph is going up. The other limit, as x approaches -2 on the right, that's near it at a vertical asymptote on its right. So if we look at the right-hand side of that vertical asymptote, just immediately to the right of it, the graph is going down. So that's a negative infinity on that limit. The other unique thing this graph has is it does not have a horizontal asymptote. What it has is an asymptote that's a slanted line. And we are going to learn how to find those in a later lesson. So let's take a look at all the different pieces of a rational graph that we are going to find. So first step, always, always, always factor first. Okay, we always, always, always want to factor this first. So if we take this numerator and factor it, it has 3 terms, no greatest common factor. We need its magic numbers. Its magic numbers need to multiply to be 2 times 4 or 8. And they need to add up to be 9, that term in the middle. So those numbers have to be 1 and 8. So we leave the 2x squared. We add 1x, add 8x, and then add 4. This 9x got split into 2 terms based on those magic numbers. And whatever variable the middle term has on, we put on those values as well. Now that we have 4 terms, we can group and greatest common. Group, group. 2x squared plus 1x, their greatest common factor is x. So as we divide out an x from each of those, we get 2x plus 1. Bring down the sign between the groups. 8x plus 4 has a greatest common factor of 4. Divide each of those terms by 4. We get 2x plus 1. So that numerator factors as 2x plus 1 times x plus 4. Now, go to the denominator. And that denominator has no greatest common factor. It has 3 terms. So for its magic numbers, they need to multiply to be negative 8. And they need to add up to be positive 2. Those numbers would be 2 and 4. We need the 2 to be negative so that the 8 product is negative, and so the adding is still positive 2. Now, the nice thing here is that because there is a 1 coefficient on the x squared, we can immediately factor this, meaning its factors are x minus 2 times x plus 4. Only works when the coefficient in front of the x squared is 1. Then that numerator factored as 2x plus 1 times x plus 4. So here is our factored form. And if you look, you see that there are factors that are alike in the numerator and denominator. That x plus 4 factor is in both the numerator and the denominator, so we can divide it out. Remember, when we divide out, the result is 1. So we have on top 2x plus 1. We have on bottom x minus 2. And this is completely simplified factored form. Now, we're going to use this form and the factors to do lots of things for this example. So, first thing we want to talk about are wholes. Wholes such as the one we had in that graph on the bottom left on the front page. A hole in the graph. And wholes occur when the same factor is in the numerator and the denominator, as in it divides out. So to find where the hole is actually located, we set that factor equal to 0 to find its x value. So to find that x value, we set x plus 4 equal to 0, and we solve for x. So x is equal to negative 4. Now, what we can do from here is we need to find the y value. The y value will depend on what is in the equation. Okay, so we take this to find its y value. We plug the x value in to the simplified factored form. So that simplified factored form is 2x plus 1 over x minus 2. We have the x, it's negative 4, so plug in that negative 4. Once we work that out, we will have our y value. So that y value, 2 times negative 4 is negative 8, plus 1 is negative 7. Negative 4 minus 2 is negative 6. Negative over negative is a positive. So our whole is at negative 4, comma, positive 7 over 6. So we took the x value we found from the factor, plugged it in to the simplified factored form to find that y value. So we found the first thing we needed. Our whole is at negative 4, 7 over 6. So if you will go to, what's it going to be, page 4 of this set of notes, you see the graph of example 1. First thing it asks you for is the whole. The whole is -4, 7/6, and we'll plot that point. -1, 2, 3, 4. 7/6 is just a little more than 1. So our whole is just, it's going to be a positive. The whole is just a little bit bigger than 1, so our whole is right here. And there's the first piece of this graph. Now, let's go back to page 2. Let's talk about the roots. The roots are the solutions to the top, or the numerator. These are the x-intercepts. And just like with polynomial functions that we did in the last unit, we set the factors equal to 0 in order to solve. So set the numerator factors equal to 0 and solve. The answers are points on the graph. The graphs must pass through any roots we find, and the graph cannot cross the x-axis anywhere else. So the factor we have remaining in the top is 2x plus 1. Take that 2x plus 1, set it equal to 0. So 2x is equal to -1. X is equal to -1/2. So our graph will cross the x-axis at -1/2. We need to write that as an ordered pair point. The x is -1/2, and the y is 0. So the root of this equation is -1/2, 0. So let's go to page 4, and where it says roots, -1/2, 0. So this is going to cross the x-axis at -1/2, halfway between 0 and -1. Now, something that our polynomial functions last unit did not have are vertical asymptotes. We saw lots of examples of those on the front page. Vertical asymptotes are lines that the graph will approach but not cross. It's a boundary line. The graph will come close but never cross. So they happen where the graph is undefined, and it's undefined because the denominator is equal to 0. The denominator of a fraction is equal to 0. Any number over 0 is undefined. That's what causes the vertical asymptotes. So we take the factors in the denominator, set equal to 0. So our denominator is x minus 2. Set that equal to 0 and solve. That is x equals 2. That is the equation of the line. We can't just say 2, has to be x equals 2. And this is our vertical asymptote. Our vertical asymptote is at x equals 2. So jump to page 4. Vertical asymptote is the line x equals 2. Then draw that line. Draw your asymptotes as dashed lines. They're not part of the graph, but we're going to use them to guide the graph. Now, let's go to the top of page 3. Tangent and together. T is for two things. Tangent, together. It's in that order on purpose. Tangent is on top because it involves the top. Tangent is on the bottom, together is on the bottom because it involves the together. Okay? So, tangent and together happen with multiplicities of 2. That word multiplicities is how many factors of it exist. So a multiplicity of 2 means a squared factor. Okay, so what will happen? An x squared term alone or a squared factor like x plus 5 in parentheses with a square. So some examples of squared factors would be x squared as its own factor, or x plus 3 in parentheses all squared. Things that are not a multiplicity of 2 are x squared plus 2x. That x squared is added, it's not multiplied, so it's not a factor. Same thing in 2x squared plus x minus 5. That 2x squared is not a factor of the whole thing, so that's a no, that is not a multiplicity of 2. And here's what happens with tangent and together. They give some clues. There's a tangent in the numerator. It's a squared factor in the numerator. Just like with polynomials, that is a tangent root. It's tangent to the x-axis. That is the double root bounce that we saw with polynomials. So if we look at this piece of a rational function here, we have a root crosses the x-axis at x equals -3. That means x plus 3 was a factor, and because of the tangent bounce, that factor was squared. Just like in polynomials, when we had the factor squared, it made the tangent bounce on the graph. The other thing that a squared factor, a multiplicity of 2, can happen is in the denominator. If it happens in the denominator, we call that a together. What that means is, because this factor is in the denominator, it affected the vertical asymptotes. So the graph will come together at that asymptote, as in both sides go up or both sides go down. So we have in this graph a vertical asymptote at x equaling 0. That means x was a factor in the denominator. And because both ends of this graph go down, that's the together. This is what the together looks like. Both sides of that asymptote, left side and right side, face the same way. So that x factor in the denominator, in the bottom, will be squared. Now, considering our equation, it's up here at the top of the page. There's your original factored out, and here's your simplified factored form. There are no factors that are squared. So there is none, not a tangent together here, because no factor, once it's in factored form, no factor is squared. There is no multiplicity, no powers on the factors. So on page 4, when this asks for tangent together, there is none here. Now, let's talk about end behavior. Let's go to the bottom of page 3, end behavior. This is how the graph looks on the ends of the far left side and the far right side. We use the degree of the numerator and denominator. We compare those to decide on one of 3 options, okay? Either the degree on top is high and the degree on bottom is low. High over low, there's what we call a slant asymptote. There's not a horizontal in that case. If it's low over high, meaning the degree in the top is low, the degree on the bottom is high, there is a horizontal asymptote at y equals 0, which is on the x-axis. If the degrees are the same, we divide their leading coefficients, and that creates a horizontal asymptote at the line y equals a over b. A and b being the lead coefficients. So there's a little bit of poetry. Go ahead, tell your English teachers we did some poetry in math. High over low, slant you go, creates the slant asymptote. Low over high, 0 equals y, which is also y equals 0, which is the x-axis. If the degrees are the same, play the coefficient game, meaning divide the coefficients. So high over low, slant we go. Low over high, 0 equals y. Degrees are the same, play the coefficient game. So if we look at our example, we look at the degree. Okay, remember the degree of the polynomial is its highest power of x. And to find the degree, I would use the original unfactored form, because it's going to be a little bit more direct that way. Okay, so our equation, original factor, unfactored form, that degree in the numerator, is 2 second power. In the denominator, that degree is 2 second power. So these degrees here, we have a degree 2 over a degree 2, so that means they are the same. And when they are the same, we play the coefficient game. So with those being the same, we do y equals a over b, a being the lead coefficient on top, that's 2. B, the lead coefficient on the bottom, that's 1. And so that coefficient game gives us a horizontal asymptote at y equals 2. Horizontal asymptote at y equals 2. So, on page 4, in behavior, HA for horizontal asymptote at y equals 2. And then sketch that horizontal asymptote at y equals 2. Now, let's do the last piece. Oh, no, it's on this page. The last piece is the y-intercept of the graph, just like any other equation. The y-intercept of the graph, we plug in x equals 0. And again, to do this, I would use the original equation, as in the unfactored form. And here's why. When we plug in 0 to the unfactored original form, 2x squared is 0. 2 squared plus 9x, 9 times 0 is 0, plus 4. That's just 4. Over, in the bottom, the same things happen. 0 squared is 0, plus 2 times 0 is 0, minus 8. So that y-intercept is 4 over negative 8, or negative 1/2. The y-intercept is a point on the graph. So our y-intercept is x equaling 0, y being negative 1/2. Okay. If you use the original form, all you're looking at is the constants. In this original form, everything with an x zeroes out, leaving us 4 over negative 8. It's a little bit easier than plugging it in to factored form. I really wanted to erase that. So, on our graph, y-intercept, write it as a point. 0, comma, -1/2, and we will plot that point on the y-axis at -1/2. Now, this is enough to draw this graph. And you're probably looking at this going, there's no way. Well, there is a way, okay? What we know is that the graph will not cross a vertical asymptote ever. And the graph on the ends, far left and right, has to approach that horizontal asymptote. So, and we also have to connect all of the pieces in one section. So, what that tells us over here in the bottom left is that these three pieces, the whole, that x-intercept, and that y-intercept, have to get connected. So, we know that we don't cross a vertical asymptote. As we go right to left, those points are arranged so that we're going down. So we continue going down towards that asymptote. Then in this piece on the far left, it's that end behavior. We approach that horizontal asymptote. So from this hole to the left, we approach that horizontal asymptote. And this is one piece of our graph. Now, there is another piece. In rational functions, there's always a piece of the graph on each side of every vertical asymptote. Left to right, there is a piece on every side of every asymptote. So, we'll have a piece either in the top or in the bottom on the other side. We don't have any points, any holes, any information there. But what we do know is because there was not a tangent or a together, since there was not a together, the sides of the vertical asymptotes go opposite directions. Okay, they don't come together on the same end, it's backwards. So on the left of this vertical asymptote, the graph was going down. And that's going to mean that on the right, the graph will go up. So our graph on the right of this asymptote faces up. So it will make that curve not crossing either asymptote. We'll make this curve in the other section. Now, we don't have any information on specific points there, and that's okay. We do need to draw that other section because it does exist. And one last thing here, let's talk about the domain of this graph. Domains break up at holes and at vertical asymptotes. So we start here on the left at -infinity. We go until we get to that first break, which is this hole at x equaling -4. So that will break at -4. Open up a new interval. We start over again at the other side of -4. And we go until the next break, which happens to be that vertical asymptote, which was at x equaling 2. So we break again at 2. Union, open a new interval. We start over again on the other side of 2. And we go to positive infinity. Because of the hole in the vertical asymptote, we have breaks in the domain. A hole causing this break at -4 and a vertical asymptote causing the break at 2. All right, there's the explanation in example 1. Examples 2 and 3, the rest of this will be on another video. Thanks, y'all.